My name is Richard Grills. I'm the Technical Director for SLM Solutions in North America, featured in the video there. A helicopter's dynamic system is subject to very high fatigue loads. Choices of materials, choice of process is critical to meet numerous requirements to ensure high security and reliability at the best operating cost for the customer. Today's featured speaker will give an overview of the different materials and processes involved in the dynamic system and the main drivers for their development. Daniel Lecoureux is currently an Airbus Group executive expert on metallic materials and processes and has led the additive manufacturing network for Airbus Group. He was also chairman of Airbus Research and Technology Network for Metallic Technologies. He's involved in different technical committees of official bodies, universities, and technical events as a scientist. Everybody please welcome Daniel Lecoureux.
Okay. So, let me introduce. So, I'm Daniel Lecoureux from Airbus Helicopter. So, Airbus Helicopter is one of the main company of Airbus Group, which is where we have Airbus Aircraft, Airbus Defence and Space, and Airbus Helicopter. So, as a glance for introducing Airbus Helicopter, we have more or less 2.5 billion of order, 30 customer centers around the world, and more than 3,000 operators around the world as well. So, what's the main also characteristic of helicopters versus Airbus aircraft? Up to 90% of our customers are less than 5 aircraft. That means there's a lot of different aircraft, different helicopters, a lot of customization beside that. So here we have we have five main production centers. The main one is at Marignane, where I'm located near Mediterranean Sea. Paris-Le Bourget, where we are manufacturing mainly blades. Donauwörth, near Munich. And Kassel, which is a ground test center. And we have another unit now in Spain. So our main product, about a civil mission, we have a lot of emergency medical applications, search and rescue, VIP also, it's one of our business market also. Offshore, it's the main business, and also law enforcement. For military aircraft, so we have different type of helicopters, scout, attack, search and rescue, sea flight, and so on. Just about our priorities about material and general priority as Airbus Helicopter. So first, customer satisfaction. So we are here to offer reliable and efficient product and support for service worldwide. After quality and safety, it's one of the main topics for us. Working on that is to have a very high level of quality and safety. And so after the competitiveness of the company, which include to proceed our innovation roadmap on material, process, and other products. So it is what I would like to explain how how this policy impact also the choice of the material and processes for a helicopter dynamic system. So here it's an overview about all the mechanic dynamic system on helicopters. So as a glance, you can see that there are a lot of type of material which are used for rotor or for gearbox and also for suspension on blades as well. So mainly titanium, stainless steel, metal matrix composite, I will explain what it is, aluminum, Inconel, but also composite material are used for dynamic system. So lot of type of material, lot of shape different and function to assure. So the technology for the dynamic system, so it's one of the main differentiation for an helicopter manufacturers. And so at Airbus Helicopter, we have developed and we continue to develop this new concept for better safety and reliability. So material and process is a key point for the success of that. So what are the main stakes for choosing material and processes for an helicopter, for a dynamic system? We have to cope with the different constraints as a security, reliability, acquisition cost, operating cost, the green also is very important now, and the performance. So the main challenge for us, for me as a leader of metallic material and processes, is to find the good balance between all the different constraints in order to have the optimized design for the helicopter. So now have a look about the technical requirement, how we manage that. So I take all the drivers I've shown just before. I put what are the design challenges to cope with the drivers and what are the impact on material and processes. For performances, so here for a driving system, so we have to transfer high loaded and to have a very efficient of the system. For example, a gearbox on a Super Puma, we have 2 megawatt in 300 kilo. So that means the choice of the material is very important. So we need to have high hardness surface, low friction surface, and high specific strength material. For the safety, so we have some constraints concerning the operating after oil loss. So we have to prove that the helicopter is able to fly after oil loss. And we have also to prove that we have a damage tolerance design. So that means we have an impact on the ice temperature strength, it's a part of the qualification, and also the propagation and delta K for the initiation of the cracks. Operating cost, that means easy to maintain design, robust design. So there's also impact about the material and process for fatigue, endurance, corrosion, and also to include into the design if the part will be repairable or not. Competitiveness, so it's the domain of recurrent cost and non-recurring cost. So comparing to the market target, and to have a better function integration and for weight saving. And also for green. So here green is more generic thematic, including noise and vibration reduction, fuel reduction, and reach constraints. So here we have to show low roughness, accurate machining. It's an impact on the vibration and the noise for the gearbox, for example. Friction coating for fuel reduction, and reach, it's all the green surface we can develop in parallel. And now, how we have, what are our solutions, taken into account the performance goal we have here, and here, the constraints about material. So, high safety and reliability. So that means we have to choose material for functional integration, bearing race and gear. I will give you some examples just after. High contact pressure, 1 and 2 gigapascal on the gear teeth. So we have to have also no propagation of cracks from a spiling. So our choice was deep nitriding process. Pitting resistance. So here it's a great high accuracy about dimensional on teeth and bearing race. So it's all the process behind that is to master the grinding process on NITRIDED steel. Low acquisition costs, so here also we have proved that this process, deep nitriding, is cost effective comparing to case hardening. High efficiency of the gearbox. So here's all the work we have done on the super finishing and interior coating. And operating after oil loss. So the specification for a military aircraft is 1 hour. So for rotor now. So the performance goal we have to reach is low weight and low drag, taken into account high loaded. So here we will see some example of function integration we have made. For freighting, it's one of the main constraints about dynamic system. So taken into account high deviation, deflection on the part. So to develop hard coating with some ductility on the coating. Corrosion resistance, so that's why we have also stainless steel and titanium on your rotor hubs. Low acquisition cost is a near shape blank, high speed machining, and so on. And high safety, it's all the topics concerning the low DADN propagation and high fatigue limit with a KT. I will give you some example of that. Now. So here's some example about gearbox. So here's an example for Super Puma and Tiger. So the material we have chosen is in steels, chromium, molybdenum, vanadium steel, alloy steel. So the deep nitriding process is a process where we put the part more than 100 hours into a furnace. And now we have more or less at 200 hours into the furnace in order to have the thickness of the nitrided layer. The thickness we can reach after 100 hours is 0.75 millimeter. So it's not so high. So into the part, as I said just before, the principle to reduce the weight and to have a good efficiency is to integrate into the same part bearing track. And here you have an example with three bevel gears and gears. So in order to manufacture that, it's not a problem but the problem now is to keep sufficient tolerances in order to be able to grind the part after that, and to keep all the geometry of the final part. So the tolerances we have to reach is about 6 microns, and for bearing race is less than the micron. So that means it's a specific knowledge about the grinding, and to be clear, that after heat treatment, the operator has only 0.2 millimeter in order to reach all these tolerances. So it's very, very tough work. So, but thanks to this technology, we are able, with this material, with a low temperature, with a high temperature, but the process is lower than the temperature, the temper. We are able to design very thin part without any very high distortion, and to integrate bearing track into the material due to the fact that we have a good hardness of the material on the layer. By the way, it was possible, as a reference of carburizing, to multiply by 2 the endurance on the bearing, and to multiply by 3, for the gear, and multiply by 3 the endurance on the bearing. So at the end, so the process is cheaper than carburizing. We have weight saving, and we have demonstrated with this process we are able to run 1 hour after oil loss. So if there's some volunteer to test it with their car, so let me know. Huh? And the results after also. So for rotors, so it's a different material. We have the evolution of the material, sorry. The evolution of the material which has been used on the rotor hub. So starting from a classical low alloy steel, and now we have moved to 55 pH with stainless steel, with a higher resistance, corrosion resistance with Marval, and now we have also the higher resistance with 55 pH. So in the future we are looking for stainless steel with higher resistance as a MLX-17. So one of the main development we have made is to make function integration of this type of part. Here it's a part, it's a mast for squirrel helicopter. We have integrated for the next following generation all the gearson into the mast. And we have also, for the Super Puma, integrated the hub with the mast. So it's a lot of also challenge in order to master all this type of technology for machining, mainly for machining, in order to keep the good tolerances and the good property of the surface. So for example, if you are looking for what are the main drivers for the designer, depending on the different area of the mast, we have to take into account the fretting condition on this area. Here you have also fretting because it's the bearing zone. Here we have to take the fatigue, damage tolerance. We can have hurt, scratch, and so on in this area. So it has been taken into account into the qualification of the material also. And also some feature like that where we can have to take into account the wear and the KT and the fretting zone as well. So it's very complex to design and very complex also to machine after in order to reach all this specification and to apply all the special process to protect this surface. So some example for hub now, for rotor hub and sleeves. So here also it's an evolution of the material, starting from the first generation where we have implemented titanium into the hub and the sleeve. And after we have moved to high strength titanium. Next generation, new titanium, metal matrix composite titanium or aluminum, but also composite material. The last generation of our helicopter, the H160, has a composite thermoplastic hub now. So here also there's some stakes and some to master the good design and to develop also all the protection for this type of parts. So here you have some area where we have fretting, the fatigue with KT. The roughness is very important, mainly for titanium. It's a main driver for the fatigue, and so on. But what we can also say that even if we have improved the mechanical property by moving from T6.4 to T10.3, in the fretting area, we have more or less the same characteristic of the material. So it is why we have also developed some material as a metal matrix composite, and I think we are the only one who, which have this type of part flying. So metal matrix composite, we have developed its aluminum alloy with silicon carbide particles. The particles are around 6 to 8 micron. So it's a powder metallurgy system. And so with that, we are able to manufacture different parts. And there's a lot of application now on the rotor hubs for blades in many helicopters. Blades, this part. So the rotating star, this one, and also non-rotating, and the seizure also. So there's a lot of application for this material. Why? If you compare here the mechanical properties of the material, you can see that MMC material, at least, has very good specific behavior regarding classical aluminum alloy, even 55 pH, and we are more or less equivalent to a titanium, but with the density of the aluminum. So now, what are the vision to go forward? So the main driver for the material, for new material and so on, it will be following. For which it's a cadmium and chromium substitution. So in order to have the green product. Weight saving, so to work on the high specific characteristics material, and new MMC material. What is very interesting with MMC material, it's a tailorable, we can tailor the mechanical properties of the material by changing the alloy or the percentage of the reinforcement. So it's very interesting to continue to develop this type of material. So also to develop new coating and also to predict the degradation mode for fretting. So in order to improve the DMC. For corrosion resistance, to corrosion propagation, fatigue corrosion, and under multi-axial load, so for the TBO. For tribology, it's low friction coating, so for operating cost and green, and Toldom also to work on the material, new material for delta K and delta I behavior. So that means it's necessary to develop a new way to develop a material and to qualify a material. So up to now, how we were working. So we have a specification from the customer, for example, oil loss, weight, saving, TBO, and so on. And after we are trying to find the good architecture of the gearbox on the driving system. From that, we have a design concept goal in order to reach the specification, and so to make some macro material characterization to do that. And after, we are going more deeply to define what are the mechanical characteristics linked to the general mechanical property of the material. After, we can go deeper in the structure. So here we are on the scale of 100 micron. And after, we try to explain the structure by the precipitation. So we are on the scale of a submicron. And after, we are going we can go up to the atomic structure. We are at the nanoscale. So here, now, if I have the new function to assure, what kind of material I have to develop? So the first challenge should be to understand what is the relationship between the nano up to the macro. It's a retro-engineering. And from that, it should be possible, I know it's possible, some of them, to know exactly what I have to change at this level in order to reach all the specification for the new design and function. So it's a new challenge for metallic material development. So some trends for the development. So new NITRIDED material for enhanced property, coating for pitting or erosion protection. So PVD could be one of the process. So safe assembly concept. So magnetic pulse welding, linear friction welding could be also some process which are interesting for some parts. Powder metallurgy, as I said, it's for me, it's the future of the metallic materials. To continue to work on enhanced stainless steel. Even if stainless steel, we have some issue about corrosion with the stainless steel. Laser shot peening, it's a very interesting process in order to improve the surface and the behavior of the material. Additive manufacturing is one part of the process, but with a lot of challenge for application for fatigue. It was the speech of this morning. And to continue to work on enhanced repair solution. Okay, so as a conclusion, so all the the design, it's clearly a collaboration between mechanical engineering and material and process expert. And model simulation is very important for the future to reduce time to market and NRC. And so research and activity should continue mainly on stainless steel, titanium, MMC material, and surface preparation as well. And composite, because it's also one of the key players for the future. So here's the end of my talk. So I'm open to answer to a question. Thank you for your attention.
Do you have any questions for Daniel?
Daniel, I didn't see in your presentation what the density improvement was for the metal matrix composites in the NH90 hub systems. Is it comparable to aluminum? I didn't see in the presentation if you showed a weight savings or a density change but for the use of metal matrix composites, specifically the silicon carbide in aluminum. Can you comment on that?
I haven't the figure, but yes, we have weight saving and cost saving by using this type of material. Most of these parts with metal matrix composite are net shape parts. There's no lot of machining after. We machine only the functional surface. So even if this material is not so easy to machine, so at the end the cost is better. And so, yes, we are, and due to the fact that the performance is better, as I said, this material is like a titanium one. So we have weight saving as well. Okay, it's answer to your question.
I have a question about cadmium chromium's environmentally friendly green moment. How exactly is that more environmentally friendly versus competitors?
So we have yes. So about chromium, where we have chromium, we have chromium on the chromic acid anodizing, on the sealing of the chromic acid anodizing. We have chromium on a chemical process, allodyne, for example, and we have also chromium for sealing of the cadmium coating. So for that, and also on the primer. Don't forget the primer also, where we have a lot of chromium. So more or less, we have found a solution for all the process. So I can say it, it's TSA, tartaric sulfuric anodizing for chromic acid anodizing, or PSA, phosphoric sulfuric anodizing for CA for bonding. So we have the solution. For primer, yes, at Airbus Helicopter we have a solution also with one supplier. The main remaining cadmium, we have also zinc nickel. Okay. The remaining problem issue mainly is halodine, where we haven't the good solution up to now. So we are working on this. Does that answer to your question?
Anyone else with a question? Okay.
Okay. So, finish. Thank you.
Daniel, thank you very much. Merci de partager votre expertise.
Oh.
All right, with us. Thank you for sharing your expertise with us. And we do have a token of our appreciation for you as well. So thank you very much. We appreciate you being here at AeroDef. Merci. Thank you.